Hello everyone, welcome back. We start our second session with Professor Jeronimo R from the Institute of Physics, UC Santiago, Chile, and Center for Nanoscale Technology and Advanced Materials. Thank you, Jeronimo. You have the power.
Thank you very much. We have a passing slide.
El mouse.
The mouse. Okay. Sorry. Your coffee.
Yes.
Thank you for the organizer for accepting my talk. I would like to give a perspective of spins, quantum bits in solid state, and how can we use them for quantum computation. Quantum computation is not my day-of-day research. I'm more in quantum metrology, okay? But since I got the impression that fundamental things are being discussed in this conference, I would like to present what we have done in the perspective of quantum computation, okay? I'm going to present you a system where we can isolate a single electronic spin. And this is not easy at all. I will show why. But imagine we can have access to a single electronic spin, meaning that we can prepare its state and also control its state by rotations and so on. We can do things such as sensing. This is my main day-to-day research, quantum metrology. For example, we can sense magnetic fields through signal interactions and so on. Okay? But in addition, as you know, this quantum bit can have two states. It is spin one half, can be spin up, spin down, and it's quantum in nature, and it can be described by a superposition by a wave function, right? Where this phase is very important for us. Actually, in this phase, and especially when you consider many qubits, in this phase relies the power of quantum computation, okay? But it's actually very difficult to have many qubits. And through the talk, I would like to give a sense of how difficult it is, at least in the system we work with. Just to motivate, because I will discuss about basic elements of quantum computation, there's two algorithms in quantum computation that performs better, one can say, than classical computers. One is the searching on a database, the Grover algorithm, where the number of operations to find something in this database is scaled as n/2 in a classical computer, where for a classical quantum computer it scales as the square root of the number of items in the database. But the striking algorithm in quantum computation is factorizing a number. So imagine you have a 1,000-digit number, okay? For a classical computer to find the prime numbers, okay, will take 10 million billion years, okay? Whereas for a quantum computer will take 20 minutes. Now, we need many qubits, much more than 1,000 qubits to do this job, okay? And through the talk, I would like to present you the qubits we have able to control, which are 3. Okay? So this will be the outline of my presentation. I will briefly discuss the elements of quantum computation. I will introduce to the electronic spin in diamond, and then also to some hidden spins, nuclear spins, that usually don't interact with us because they are very small, but actually they have advantages over electronic spins. And then a topic that is basically a headache for us, which is the coherence, and what will be the role of the spin-photon entanglement in this story. So to start with the elements of quantum computation, there are 7 criteria, 5 plus 2, because Di Vincenzo added 2 after he discussed the first 5. We need to have a scalable physical system with well-characterized qubits. These are the requirements for quantum computation. Now, this is already super difficult because of the word scalar. Second, we need to have the ability to initialize the state of the qubit, okay, into some state. We need good coherence, and I will explain what we know by decoherence and how do we address that or avoid decoherence. We need a set of universal quantum gates, a one qubit gate, which can be sort of a rotation of a spin, and a CNOT gate, which I'm going to present. A qubit-specific measurement capability, okay, given a matrix, density matrix system describing a spin 1/2 qubit, okay. If we would like to get zero state, we would like to measure basically P with 100% probability. And in addition, okay, and I think later, basically, the researcher realized that scaling this system is very difficult. Here it is two criteria: the ability to interconnect stationary and flying qubits, okay, and the ability to faithfully transmit flying qubits between specific locations. Okay, so which are the candidates for quantum computation? I will discuss basically candidates in solid states. We have quantum dots, right? Basically, you isolate electrons with some electrodes around, and it turns out that those quantum dots has very short coherence time, which will be very important, 20 nanoseconds, if you cool down the sample to cryogenic temperatures. On the other hand, we have color centers in diamond, and this will be the main topic of my talk. They have very good coherence times, even at room temperature. 1 millisecond, 2 milliseconds is a lot of time for when we talk about coherence of electronic spins. Now, not all color centers in diamond are useful. There's a similar defect or color center, the silicon-vacancy center in diamond, that is very similar. The first one is nitrogen-vacancy, this one is silicon-vacancy, and there's no coherence observed, right? Whereas it is predicted, actually. Okay, so I will discuss about the electronic spins. Later I will discuss about the nuclear spin and what are the roles for quantum computation. And at the end, I'll discuss briefly about the flying qubits. The system we work with, right, is a defect in diamond, which is composed of vacancy, a missing carbon in diamond, and a nitrogen, substitutional nitrogen next to this vacancy. This can be sort of a molecule, okay? And actually you can deduce all the orbital states and so on, the properties using elements of molecular theory, such as group theory and so on. The message here is that it's stable at room temperature, its coherence is independent on temperature, actually. Well, it gets much better below 2 Kelvin, right? But the good thing about these defects in diamond is that they are trapped by nature. We don't need complicated things such as ion traps, where you have complicated experimental designs in order to keep the qubits in place. They are basically in place by nature. They can rotate, so you don't have broadening of their energy by rotational degrees of freedom. And well, first I'm going to discuss about the good things and then the bad things, right? The other good thing is that we can see single electronic spins just using confocal microscopy. And this is something very difficult to believe to people that did experiments 40, 50 years ago, okay? We are sure we have single emitter. There's a single electron going up and down through all the states that are present in the defect. And why we know that is because we observe the second order correlation measurements. That means that if you get a click on a detector, meaning getting a photon, okay, you need to at least wait for the spontaneous decay again to measure a second photon. Okay? So basically, there will be this spontaneous decay lifetime, which is on the order of 10 nanoseconds here. So within 10 nanoseconds, you're not able to detect 2 photons. Okay? And that means that this signal basically goes down at 0 delay between the photons arriving. Okay, but it's even better. We have a solid diamond, there's a valence band, a conduction band. We create this defect. The ground state of this defect is 2.2 electron volts away from the valence band, which is very good in terms of temperature stability. But also the optical excited state, the first optical excited state, is within the gap of the diamond and far away from the valence band. That means that the optical excited state is also stable, in the sense that if you shine a green laser, promote from the ground state to the excited state, from the excited state will come back to the ground state of the defect of this system. Okay? Here's a simplified structure of the centers. I have the ground state, which is actually spin 1/2, 2 amperes electrons, okay, forming triplets and singlets. The triplet is here, the singlet is over there, right? And it has an amazing property, which is if you shine a green laser, okay, and you start on the projection m is equal 0, you're going to cycle between the ground and excited state, okay? However, if you start from plus or minus 1 projection of the spin, you go to the excited state, you come back again to plus or minus, but sometimes you get trapped in this metastable state, which has a lifetime of 300 nanoseconds. And the only way to come back to the ground state is to the m is equal 0 state. Therefore, if you apply a green laser, right, you basically optically pump the spin into m is equal 0. Which is truly amazing because basically you are preparing a nuclear spin at room temperature. Okay? And that's basically one of the differential requirements. You need to have the ability to prepare something. I didn't mention, well I mentioned now, the difference in energy between 0 and plus or minus 1 is basically 3 gigahertz, right? If you estimate what will be the equivalent temperature for that, okay, is very small. 1 degree Kelvin is equivalent to 20 gigahertz. Okay, so 300 Kelvin is equivalent to you multiply, right? So basically, at room temperature, all this is populated by boson. Okay, but just by shining a green laser, we can basically pump into one state. It has a spin Hamiltonian. Sorry for the equation, okay? But the message is that we have the ability to prepare the state. I have an animation that basically you can go from that to there, but we have problem with the format, so now we have to start at the end of the animation only. It's even better, so we can prepare it, okay? This is not at all simple, but we can actually read the spin state. We can measure the spin state. And basically this is done in the following sense. Since you start from 0 and you go up and then go back, in 10 nanoseconds you get a photon. Only if you start from 0. But if you start from 1 or minus 1, sometimes you get trapped on the singlet. During 300 nanoseconds you don't get any photon. Right? So here's a time trace of the cones. If you start from 0, you get much more photons than if you start from plus or minus 1. So just by counting photons, we can measure the electronic spin state. Okay? In addition, this distance, for example, between 0 and 1 is around 3 gigahertz. We can apply microwave pulse radiation, and we can basically perform radio oscillations. Here you have a graph of the fluorescence, actually, of the defect as a function of the duration of this microwave pulse. If the pulse is 0, basically the electron remains in m is equal 0. That's associated with a lot of photons. But as you start rotating the electronic spin, you go from 0 to 1, which has less photons, okay, and that's the over there. Actually, you have a complex. And if you do it in the middle, 10 minutes, you get a superposition state. Okay, that was the electronic spin. I will now discuss about the nuclear spin. And there's something good about the nuclear spin, which is good and bad, which is the gyro-magnetic ratio. The gyro-magnetic ratio of the nuclear spin is thousands times smaller than the electronic spin. It's bad in the sense that it's thousands times more difficult to interact with this nuclear spin. But it's good in the sense that it will interact thousands times less with the environment, which basically causes decoherence. So in diamond, there's 1% of C13, which is a spin 1/2, okay? And actually, if you perform electronic spin resonance, you see there are several transitions, basically, that are split because there are several nuclear spins around. And we can actually address some of these states, okay, by applying microwaves which are weak enough in order to promote a transition from one particular state to another one. If the microwave is too strong, you perform transitions among all those states. Okay? Especially if they are close together. But here is an example. I'll skip that because it doesn't fit in the 10 minutes. Here's an example where I have two states of the electronic spin and one nuclear spin, which is up and down. Okay, I can characterize this as we heard before with 4 states, right? So imagine that we apply green laser. We are at the top there. We can basically polarize the electronic spin as I discussed before, right? But we cannot polarize the nuclear spin at the moment, right? It's all basically in zero, ms equals 0 electronic spin. And then we apply a selective microwave rotation, which is basically only transfer this population up. Only if the microwave is too weak. It takes time. The weaker the microwave is, the longer this transition is. Okay? We apply an RF, and now we apply a green light again, and we have prepared here basically the electronic spin in 0 and the nuclear spin in up.
Puedes usar el cursor para señalar del mouse en la presentación.
Good idea.
Ahí está. Eso.
Okay? We can actually perform CNOT gates. That means, for example, changing the state of the electron conditional to the state of the nuclear spin. Okay, here is a CNOT gate, okay, which is a basic element of differential criteria. Okay, we can also prepare more complex states with GACs, such as GAC states. Okay, but there's a problem. Okay, and the problem is decoherence. We don't have only 3 qubits, 1 electron, 2 nuclear spin. We have many of them. 1% of carbon is carbon 13, okay? So basically, this decoherence, what we'll do is basically make this phase difference, okay? Every time we perform an experiment. And actually, we don't perform one experiment, we perform millions of experiments to get one measurement, right? So, for example, for this cat, actually, it is very important that this phase remains the same, right? Here's the famous experiment. There's a particle detector there, right? And this detector activates, breaks a bottle with a poison that will kill the cat. But if the particle changes state and has a different phase, okay, the detector might actuate and the cat will be dead, okay? So what's decoherence? What's the way we we understand the coherence, imagine that you have an orchestra, and one director is basically directing all musicians, okay? At the same time, the song will sound, the piece will sound like this. That's enough. However, imagine you break up several performances. And one day the director is super enthusiastic, okay, has a different environment, different breakfast and so on. He will conduct the musicians differently. And let's say he repeats the experiment several days in a week and then sum up all of them. This is actually what we do in experiments, okay? The piece now will sound like this. You notice the difference? And it gets worse with time. Okay, that's enough. Okay, so that's the problem with the coherence. For some reason, we have to hear this again. Apparently, it was working actually. Okay, this I'll skip because I don't think I have 10 minutes still, right? But basically, the coherence change basically get worse for experiment. Okay, 3 nuclei. What about having more nuclei? I told you that we can transfer this population from that state to some of those states if this microwave is weak enough. Okay? And the weakness of this microwave, I'm illustrating with the thickness of this arrow. If we have more, basically it's splitting, you know, all the states because it has further interactions between the nuclear spin and the electron spin. The states are closer, okay? So I need even weaker microwaves. If I keep doing this, okay, the states are even closer, I need even weaker microwave, that means longer times, right? So you have many nuclei, you see what's going on, okay? So what would be ideal? To modify isotopically the content of diamond, right? Or engineer a defect with just few qubits, but then we cannot factorize a 1000-digit number with that, right? We need to basically communicate whatever quantum state we have there to some other place, okay? And that's where the role of photons comes into place. Here is the real defect. Okay, all the real states are there, reproduced by group theory and so on. That's the fluorescence spectrum. Okay, here there's a 0 photon line there. If you sum up these, there's several transitions. Okay, and in particular, there's one state A2 here that's good to perform the following experiment. If you are able to promote, and this can only be done at 4 Kelvin, if you promote your electron to the exact state A2 and let it spontaneously decay to the ground state, if it's decayed to the spin projection 1, the polarization of the photon is left. But if it decays to a spin projection down, the polarization of the photon is the opposite. Okay? And with this, basically, you can entangle the polarization of the photon to the spin state that is basically remain on the electronic spin. Okay, several amazing experiments have been performed with this system, such as unconditional quantum teleportation between distant solid state quantum beats. Nuclear spin has been used for memories. Room temperature quantum beat memory exceeded 1 second, that's a lot of time, but very soon came another result where they have nuclear spin living for 39 minutes. Okay, so to conclude, in principle, elements for quantum computation are available in solid state. However, electronic spins are not good for that. They interact too strongly with the environment. Okay, they have short coherence times. The coherence times, now taking into account some of the division criteria, where the requirement is that the coherence time should be at least 10 to the 4, 10 to the 5 times the clock time. Okay. There is flying qubit. There has been demonstration for flying qubit, basically entangling electronic spins and photons. However, the success probability, and that I didn't mention before, is 10 to the minus 7. Okay. So if you would like to basically entangle two separate systems, okay, the electronic spin states, okay, through this photon interference in a middle splitter, you will have to square that probability. Okay? So elements are there, okay, but there are some difficulties. Okay, with that I would like to acknowledge my group of students and collaborators, and thank you for your, this was an advertisement, and thank you for your attention.
We have time for a few questions. Anybody? Question?
No, it's very interesting, this room temperature effect. I want to point out that perhaps birds are able to detect the magnetic field.
Yes.
And it seems that they use something equivalent to your nitrogen defect in diamond. Not using diamonds or not using the cryptochrome. And they are able, it seems, to have a coherence time of many milliseconds. At room temperature, at 40, it's not even room temperature, it's 42 Celsius.
You're saying it's quantum?
It seems, it's not totally clear, but we have evidence, not we in our group, but collectively it exists evidence that birds do exploit the quantum mechanical effects for detecting the magnetic field using exactly the same spin trick that you know. But using an organic molecule, a macromolecule.
Right. We are aware actually because when we basically obtained this result, we were looking for systems in nature that can use magnetic fields, okay? And basically this tool is ideal to explore those systems. We didn't know that there's actually quantum. It would be good to see how they do it. How they keep coherence time. But there's actually also worms that use magnetic fields to navigate, okay? And they have a set of molecules which are magnetic, okay? They form a change, and that has been measured with this actual system.
Any other question?
This is a question I always ask experimentalists when they come up with a topic. You mentioned that it will be a tremendous improvement in, for instance, factoring, and as we don't know if there exists not polynomial time algorithms for doing that anyway, also classically, if we had enough quantum bits which would communicate. And then you mentioned, and this is a kind of, may I say, contradicting message, very humbling. I like that very much when you say it is extremely difficult to do it even on those simple things. Now, just your impression, your personal impression, do you think, I mean, so this exponential parallelization of quantum mechanics, in a sense, is counterbalanced with some kind of factor when it comes to keeping these things coherent, and maybe even greater than exponential. I mean, which if that would be the case, quantum mechanics, there wouldn't be any supremacy because you can just be parallel classical architectures which could do the same job or even better than and they're actually doing it now. I mean, so my question to you is, do you think that quantum mechanics ever, just a personal evaluation, will overcome this decoherence issue when it comes to many quantum bits, from a personal perspective?
It's actually a very good question. I feel I am more on your side, by the way you present the question, than on the side of the quantum computation community. But I have to recognize that if you would like to describe a quantum system with few qubits, to the best of my knowledge, it is not possible to perform with a classical computer. Even 10 qubits is super difficult, okay? And it's in the way you basically construct, quantum mechanics. For a 10 spin 1/2 qubit, you need matrices, diagonal line matrices that are of dimension 2 to the 10, okay, by 2 to the 10, right? So that, if you add 1 more qubit, or 2 more, or 3 more, that's not possible at all. Okay, this is my understanding. So there is a power there, okay, which might be useful. I mean, we are not that far away from having clean 10 qubit systems. People have performed, for example, 50 or 53 qubit systems, not for quantum computer, but for quantum simulation, which is a bit different. Okay, those kind of factorized, but basically you have a system, real system, that basically can simulate something, the history of something that a classical computer cannot. So maybe the value of that has to be, rethink to find some other useful application. Now, I have the feeling that we are basically following the obvious path of classical computing, okay? Where we have bits, zeros and one. Basically, we are creating the qubit. 0 up and down, and it has a superposition. So I would be very surprised that it is that obvious. Okay? I think if something useful will come out from that, I will expect to be a totally different